So let's go for it. So describing how we create an MO diagram. So I should write that there, MO diagrams. Okay, so electrons supplied by atoms are accumulated in orbitals to achieve the lowest energy configuration, subject to constraints by Pauli. Okay, so we know that the bonding configuration will be the lowest energy configuration. The anti-bonding configuration is the highest energy configuration. So our goal is to try and minimize energy. So if several degenerate orbitals exist, then electrons are added singly to each individual orbital before doubly occupying any one orbital. That's what that should say. Any one orbital, okay? If two electrons do occupy different degenerate orbitals, okay, so let's be very careful about this. So they could be degenerate, so same energy, but they are different orbitals. And so a good example of this would be like px and py, okay, for example. So a lower energy is obtained if their spins are parallel. So in other words, not paired up, but both going in the same direction, right? Which creates the triplet states. So up, down, or the superposition of either state, okay? So a triplet state in molecules actually makes a lower energy state than a singlet state. That's contrary to what you might expect. You might expect, two paired electrons being a singlet to be the lowest energy state. And that's true if that's the only option for the electrons, right? Is that they both have to occupy the exact same orbital, then the lowest energy configuration will be achieved if they're singlets. However, if there are different degenerate orbitals that the electrons can spill over into, a triplet state will be the lowest energy state, okay? So let's talk about sigma orbitals, all right? And so we've talked about sigma bonds with valence bond theory, right? We know that a sigma bond is symmetrically cylindrical about the z-axis. And you can see I've got that right here on my Mathematica file, right? We know that we create a bonding sigma orbital from constructive interference, and we create an anti-bonding sigma orbital from destructive interference. But now what we need to talk about is their symmetry, okay? So as it turns out, a bonding sigma orbital has what we call even symmetry, which in the German is Gerard, okay? And we create this even symmetry by drawing a plane through the center of the internuclear axis. So I'm drawing a line right down the internuclear axis, and I start below that line and go above that line. And if the wave function does not change signs when I go above and below that line, in other words, if they're both positive, then it's called Gerard symmetry, okay? And so our, when I earlier alluded to that we were going to use the 1 sigma g, that's where that g comes from. So our bonding sigma orbital is 1 sigma g. But now if we look at the symmetry of the anti-bonding orbital, right, we recognize that it's destructive interference. So there's a positive and a negative overlap, which is what creates the destructive interference. And it doesn't matter which one you ascribe to be positive or negative, because we know since it's this anti-bonding orbital with destructive interference, it has to change signs. That's why it has that destructive interference. So that is called odd symmetry or un-Gerard, and that's designates the anti-bonding orbital as 1 sigma u. Okay? So now we create a molecular orbital diagram. So I'm going to start on the left by kind of showing you like my, this is a diagram from my Gen Chem notes. And then I'll show you the more simplified version of it on the right there. Okay, so we have our 1s electrons, right? And I've got my model in front of me. So if I back up here, you can see exactly what this is creating, right? We've got two separate 1s electrons, which are given right here. And, you know, the reference of those is, I'll remind you, like if I look at my bound state, okay, right? The reference of that is given as the 0 line. So I could say 1s down here and 1s down here. And now down here, I make a sigma, and I'll just use the nomenclature that we talked about, the 1 sigma g. But you notice right here in my Gen Chem notes, it says sigma 1s. So, right, it's the 1 sigma g. Okay. But this diagram, it literally has its origins from this Lennard-Jones potential well. We recognize at infinite separation, the energy is just equal to the 1s energy, right? And there is some minimum energy, okay? We also remember that there's an antibonding state, right? This repulsive antibonding state that we now know is the 1 sigma u. And if I do what's called this vertical transition where I go straight up, then that line right there, which we can see right here, corresponds not to the minimum, it just corresponds to the vertical transition of the antibonding state. In this case, sigma star 1s. So oftentimes if we see a star, that also denotes antibonding. And we have one electron from our hydrogen 1s. We have another electron from the hydrogen 1s. And those combine to pair up because they have to, right? If I put two electrons in this bond, we still are subject to constraints by Pauli. So the H2 has to make a singlet state, right? And so we could write our H2 molecular electron configuration as 1 sigma G2. Okay, so that's how we would write our molecular electron configuration. And we recognize that it is making a singlet state because they're paired up. So the simplified diagram looks something like this, where we've got the H1s and the H1s, and the 1 sigma G and the 1 sigma U. We know that there's an electron over here, and there's an electron over here, and they spin correlate to make a singlet state, okay? So we can also use these diagrams to describe why certain molecules don't exist, okay? For example, we know H2 can exist because according to my diagram right here, it's all bonding. And so I forgot to put the formula on here, but we can come up with something called bond order, okay, which is given as the following, B, and that's going to be 1/2 times the number of, let's see, all right, bonding electrons minus the number of anti-bonding electrons. So if we do that for H2, we can see that there's 2 bonding electrons and 0 anti-bonding electrons. So B equals 1/2 times 2 minus 0, and that equals 1. And so a bond order of 1 means that, yep, it's just a single bond, H bonded to an H. Okay. He2 cannot exist. And the reason why it cannot exist is because of the following. So we know that each H1s brings 2 electrons to the table, and each H1s, of course, is a singlet state in its ground state. And so now because each H1s brings 2 electrons to the party, I've got to supply 4 electrons into my orbital diagram. So I go 1, 2 in the bonding, and I've got 2 left, and those have to go in the anti-bonding. And so now my bond order for helium-2 is going to go as 1/2 times 2 minus 2, which equals 0. So helium-2 can't exist. Okay, hopefully you remember that. And Also, if you might kind of guess, you might remember this intuitively, when you go to look at all the other noble gases, all of the other noble gases will be completely full shell. So their bonding electrons and their anti-bonding electrons will cancel out. So none of the noble gases exist as diatoms. Okay, hopefully you remember that. So moving on.